Hello and welcome to the Chapter 1 podcast on Section 5. So today we're going to be talking about uncertainty in measurement. So when we're measuring things, we want to have as an exact number as we possibly can. But a lot of times, what you have to remember in science, a lot of the numbers that we have are measured via some things, either like a scale or a ruler or a thermometer or a pH meter. These are all, numbers. And numbers in science have different meanings. It's not like math where 2 is always 2. In science and even in chemistry, a 2, in science will always have a unit of measure associated with it. So it's not just 2, it's 2 centimeters. But when I say 2 centimeters, for instance, there's a difference when I say 2 centimeters and 2.0 centimeters. It's the exact same number, but there's a lot of information you can get in terms of how it was measured, even though you might not have measured it directly yourself. So there are some numbers in science that are considered exact numbers. These are numbers like it has an infinite number of zeros that follow the decimal place, but we don't write them all. So for instance, if we're counting something, when I say there's 3 people, I mean that there's 3 exact people. It doesn't mean like there's 3.5 people or 2.5 that got rounded. It means that there is exactly that many. The other time where we have exact numbers are in inequalities. So these are when we have conversions. So like if I say that there's 100 centimeters in a meter, that means 100.000 forever equals 1.000 forever meters, and we don't write all those zeros out, but it's supposed to be an infinitely exact number. Now, most numbers that we have are not like this. Most of the numbers that we're going to deal with are what we call inexact numbers. Inexact numbers are measured, and they're uncertain because of what we call degrees of freedom or estimation. So let's say we're using this ruler, and we're going to measure this sentence. Uncertainty is due in degrees of freedom. So let's, if I drop this, if I color down as straight as I can, you can see that it doesn't fall exactly on the millimeters line. So all these little notches are millimeters. These big numbers you see here are centimeters. So if I estimate how long uncertainties due to degrees of freedom is, it's technically 62. It's at least 62 millimeters long, right? But you can notice that the red straight line I drew is actually a little bit beyond the second millimeter, right? After the 6. So this is what I mean by degrees of freedom. I'm free to estimate where this red line actually falls. And different people might interpret it in a different way. Some would say, it'd be 62.2 millimeters. Some people would call it 62.3 or only 62.1. What's important to keep in mind is that last number in our measurement are 60. Oh my God, my writing's so terrible. 62 I called it 62.2 millimeters. This last number that I wrote in really bad handwriting is actually measured. Estimated. It's my estimation of what it is, and that's what a degree of freedom is. With things like this that are non-digital measurement measuring devices, you're going to have this degree of freedom. That's where uncertainty begins. Also, what you'll find is different measuring devices have different capacities in terms of their ability to measure. Just to kind of highlight that point, I have a ruler right here. So notice here, here we have millimeters. I should hold this up so you can actually see it. And notice here we have centimeters, and then we have decimeters. So notice the difference in the notches. So depending on where the measurement falls, you can estimate in different ways depending upon the type of measuring device you have. But back to precision and accuracy. Precision and accuracy is a way to kind of evaluate your measuring device and your measurements themselves. Precision deals with like how closely a series of measurements agree with each other. So this would be something that you remeasured over and over again. Okay, I like to think of it as consistency. So in other words, you want your measuring device to kind of fall within the same number over and over again. You also want your measuring device to be accurate, and this is how close the measurement is to the true value of that of the thing you're measuring. Usually we use standards to help us kind of calibrate our measuring devices. We obviously want, you know, good accuracy and good precision. So if we kind of use throwing darts at a dartboard as an analogy, so if all 3 darts hit the bullseye, that's good accuracy and good precision. That'd be like a highly tuned measuring device. Sometimes we'll have poor accuracy but good precision. So in other words, you're missing, but you're consistently missing in the same spot. And we've all kind of had that watch that's always 5 minutes fast, or the scale at home that's like always 2 pounds heavier than it really is. So those are examples of that. And then the worst thing you can have for a measuring device is poor accuracy and poor precision, where you don't know where the numbers are going to fall. Usually measuring devices like these are broken or need to be recalibrated. This is one of the reasons why we do multiple trials, to make sure the numbers that we see are actually not only accurate but also precise. Significant figures. So this is a way for us to kind of figure out what numbers were measured, including the last measure that was estimated. Usually when we're dealing with significant figures, only the last digit in a number was estimated. Sometimes we express uncertainties with plus or minus. So depending on the device, if we know how accurate it is, we can say, for instance, if we have a scale that is plus or minus 1/100th of a gram, if I give you a measurement of 24.53 grams, technically the range is 24.52 or 24.54. So notice how I subtracted 0.01 or I added 0.01, and that gives you an idea of how accurate your measure is. Okay? But normally we usually don't include this part in our measurements, but we can take it into consideration. For instance, here we can also, again, have our degree of freedom, and we can estimate exactly, you know, if this is 30 degrees and this is 25, then we can estimate, is that 27? Is it 27? You know, is it 28? You know, 26? That would be your degree of freedom again. So not every figure you're going to actually directly measure yourself. Sometimes we're going to have to actually look at numbers, and we're going to have to figure out how many significant figures there are. Now, the number of significant figures doesn't change the value or magnitude of the number. What significant figures tells us is basically how it was measured. So for instance, if I go back and if we go to 2 centimeters and 2.0 centimeters, because of the number difference in significant figures between 2 and 2.0, the 2.0 essentially implies that that number was measured to the nearest 1/10 of a centimeter, whereas 2 centimeters implies that it was measured to the nearest centimeter. So you can, without having measured that yourself, you can look at the number of significant figures for measured values, and you can determine how accurate it actually is. This is going to be important later on when we figure out how to properly round numbers we use in calculations. But before we do that, let's go through the rules of determining the number of significant figures there are. Number 1, all non-zero digits are significant. So for instance, if I give you this as a number and ask you how many sig figs there are, which is short for significant figures, 24.55, because these are all non-zero numbers, this would be 4 significant figures. Zeros between non-zero digits are always significant as well, so these zeros between the 1 and the 5 are also significant, so they count. Even if it's a decimal place, it still counts. Zeros at the beginning of a number are never significant. They merely indicate position of the decimal point. So for instance, if I have 0.02, these zeros in front do not count, so only the 2 is considered measured. Whereas, and in this one, same thing, where only the 2 and the 6 are actually measured. These other things are just here to hold the value of the number itself. Zeros at the end of the number are significant if the number contains a decimal point. So for instance, any zeros after the decimal point and after a significant figure are significant. So here 0.0200 has 3 significant figures. This 2 and these 2 zeros are significant with 3.0 liters, because this is after the decimal point and following a significant figure, both numbers are significant. So we're implying here we measured to the nearest tenth of a liter. In this case, even though that follows the, even though it's to the right of a significant figure, it's not also to the right of a decimal point. So even though it's to the right of a significant figure, it's not to the right of the decimal point. So these zeros would not count, and this would only be one significant figure. For this one, this zero is significant, and because this zero here is between two significant figures, it is also considered significant. There are some instances where you can have infinite numbers of significant figures. So this goes back to exact numbers, as I mentioned at the beginning of the podcast. So if I'm counting things that cannot be broken into fractions, that's technically unlimited, and also numbers used in inequalities or used for conversion factors, those are also considered unlimited as well. The reason why significant figures are important is because it guides us in terms of how we round when we do math. Now, when we're dealing with significant figures, you can only be as accurate as your least accurate measure. It's kind of like similar to the analogy, you're only as strong as your weakest link. So if you project more, when you're doing calculations, if you have more significant figures than your least accurate or least significant measurement, then you're implying you measured more accurately than you really did. And there are cases where you get in a lot of trouble later on if you're not that accurate. So our least accurate measurement is always the one with the fewest number of sig figs. And when we multiply and divide, we always round to the number that we're multiplying or dividing with that has the fewest number of significant figures in them. So here, if we're calculating the area, we have our two length and width. So this number 6.221 has 4 significant figures. 5.2 only has 2 significant figures. So the 32.3492 square centimeters represents the unrounded answer. Also remember, when you're doing calculations, always include the unit of measure associated with it. Because our least accurate measure has 2 significant figures, our final answer can only have 2 significant figures. I know it seems kind of strange, but this is the proper answer. And on the AP exam, they will be checking in the free responses to make sure that you're giving the right number of sig figs. When we're doing adding and subtracting, we're looking not at significant figures, but the fewest number of decimal places. When we're adding and subtracting, we round to the fewest number of decimal places. So if I'm adding these 3 numbers together, because 83.1 has the fewest number of decimal places, even though this is my unrounded answer, my rounded answer can only have 1 decimal place. Remember, when we're rounding, guys, we look at we look one past where we're going to round, and if this number happens to be a 5 or greater, the number moves up a digit. If it's 4 or less, then the digit remains the same. And here we go again. You'll look at the leftmost digit to be removed. If the leftmost digit removed is less than 5, then the preceding number left is unchanged, and then so on. Same kind of idea. And that's it for now.